Hello and welcome back to my channel. Welcome back to the Concurrency in Go course. This is part 3 of our topic, which is weight groups. And yet again, if you haven't watched the second part of this topic, make sure to watch this video right here. Like in the previous video, at the end of each video, I'm going to provide you with a zip archive so you don't have to write all the code by hand, so you can just download that. That's why head over to that GitHub repository and download the zip archive so that you don't have to write everything by hand, so that you can follow along as we progress in this video. And in part 3 of this video, we're going to dive into even more examples, a little bit of tracing, a little bit of benchmarking, and so much more. I am super hyped, super excited. This is why let's not waste a lot of time and let's dive into this video. So in the last video, when it comes to introduction to concurrency, we talked a little bit about the Go scheduler and how it does schedule things, how it does the heavy lifting when it comes to concurrency for you. So when we use the Go keyword in front of a function, what exactly will happen is the Go scheduler will get triggered and it will try and schedule that Go routine. It will try and schedule that function somewhere on a specific thread, which is going to get run by a specific processor or CPU. However, my question is not about the Go scheduler or how it does things. My question is, when we write Go code and when we use this Go keyword in front of a function, does the code execute sequentially? Which means, does the code execute in the exact same order as we specify the Go keyword? Well, the answer is very simple. First of all, the Go scheduler doesn't know or doesn't even have any kind of idea how much work there is to be done inside each function, which means it's going to try and schedule each function on a specific thread. Now, let's say the Go scheduler has done its job. It's time for these tasks to actually execute. And when these tasks execute, it's also not guaranteed which task is going to finish first, because again, it depends on what kind of work they're doing. So the rule of thumb is, every time you write Go code, it's not guaranteed that the order in which you write your code, in which you use the Go keyword, is actually going to be sequential or execute one after the other. It has to go for the Go scheduler, and even if the Go scheduler does its best job to actually schedule that and make sure it executes as efficiently as possible, it's still not guaranteed that it's going to actually execute in the exact same order the Go scheduler actually scheduled them, which means everything is going to be executed pretty much randomly, which means you don't have to really have any kind of expectations as to what is going to be the order in which the Go routines execute. Now, all that being said, let's have a look at an example which demonstrates that. Like usual, I'm going to create a new directory right here. So let's say directory, and let's call this one Go routines order. And inside of this one, let's create new directory. Simple. As usual, let's create a file called main and package main, func main. As usual, let's create a wait group. So that's pretty simple. Let's say var WaitGroup sync.WaitGroup. Then after that, let's make sure we wait. Let's say WaitGroup.Wait. So let's, for example, go ahead and spin 10 Go routines. So let's say I from 0, I goes up to 10, and let's see I++. So let's say WaitGroup.Add, for example, 10. Let's say go func, and let's also call done before we proceed to any kind of action. So I'm going to say prefer WaitGroup.done. So let's print something fairly simple, something like from print line, let's say go routine, and let's print the ID. Let's say, for example, I+1. Also, as you can see, we have a squiggly line here. It says loop variable I captured by func literal. So what that means, it's we need to pass this over here as an argument. So I'm going to say I is going to be an end and pass I like that. If you run this example, as you can see, the order always the first. If you run it again, run it again, run it again, as you can see, the order is always different, because obviously we go from 0 up to 10, which means the Go keyword shows up sequentially. However, when we run this example, it's not sequential. It's always random. It's always in its own order. Another problem which arises when executing concurrent code is, let's say you want to preserve the order. Let's say some of the tasks can execute concurrently, can execute in parallel, but somehow you want to preserve order. You want to execute a certain amount of tasks first, then you want to execute a different amount of tasks second, and so on and so forth. So you want to preserve order. Let's say a couple of tasks, in our case, task 1 and task 2 can execute concurrently, but they don't have to execute before task 3, task 4, and task 5. So with all that being said, let's jump into another example which demonstrates that. So in the same directory which says Go routines order, I'm going to create a new directory which says preserve order, and let's, as usual, create a main file, and let's put out the main package and func main as usual. So let's imagine you have 5 tasks, right? Those tasks will eventually get executed asynchronously using the Go keyword. So I'm going to say something like func task 1, for example. And first of all, we're going to receive the wait group as an argument, which means we have to pass this as a pointer. So let's say wait group is going to be sync.WaitGroup. Then regular procedure, let's call defer using WaitGroup.Done. Then to keep things simple, let's sleep a couple of times. Let's say time.sleep, for example. Let's say time.second from the print line, for example, task 1. And let's go ahead and copy and paste this one. So let's see. Copy, paste. Now let's go ahead and change the names and the prints. So let's say this one's going to be task 2, and this is going to be task 2, and this one is going to be task 3. Also change the name to task 3. This one's going to be task 4, and this one is going to be task 4 as well. And this will be task 5, and this one is also going to be task 5. So first of all, let's create the wait group as usual. So let's say for wait group, sync.WaitGroup. Let's say WaitGroup.Add 1. So let's first of all say WaitGroup.Wait, and then let's say go task 1 and provide in the address of the wait group. Now let's go ahead and copy these 3 lines and paste it so that we can execute task number 2 and then task number 3. So as you can see, we first of all execute task number 1, then we have to wait until task number 1 is done. And then let's go ahead and copy this again, paste, and of course we can go ahead and say task number 4 right here and copy this and say task number 5 right here. Before we run this example, however, I notice here we need to add 2. So let's just go ahead and add 2 because we are executing 2 tasks, as you can see. And now we can go ahead and execute this example. And when you run this example, as you can see, after 1 second, task 1, after 1 second, task 2 and 3, after 1 second, task 4, and after another second is going to be executed task 5. If you run it again, as you can see, the order is always going to be the same, except for task 2 and task 3, they can execute whenever they want. So even if using the go keyword as we do here, you have to be careful when using wait after each individual task, because in the end, you're going to end up waiting exactly the same amount of time as if you would have executed these tasks without using any kind of asynchronous solutions like wait groups or even running it using the go keyword in front. So we had a look at a very simple example before where in a for loop, we simply execute a couple of go routines. They run in different order and all that stuff. However, they did not do quite complex work, and they were just simply printing something out, and you might say that's not fair to compare them when it comes to execution and the order in which they execute. This is why now let's have a look at another example, a little bit more complex example where we have different go routines with different workloads, if you will. So in the same directory go routines order, I'm going to create a new one called different workloads. So let's say different workloads, and as usual, let's create a main file, and then let's say package main and func main as usual. Just like in the example before, let's go ahead and create 5 tasks, which will eventually get executed using the go keyword. However, this time those tasks will have different workloads, hence the name of this example. So I'm going to say func, for example, task 1, wait group, pointer to sync.WaitGroup, and normal procedure, let's say defer WaitGroup.Done. Now let's go ahead and copy this and paste this a couple of times. And let's rename the tasks. This one is going to be task 2, this one will be task 3, and this one will be task 4, and this one will be task 5. Let's also print something out like, let's say from to print line, for example, task number 1 is done. Let's copy this, paste, and as well, let's rename these to number 5, number 4, number 3, number 2. And now, like in the previous example, let's go ahead and create a wait group. So that's fairly simple. Var wait group, sync.WaitGroup. Let's make sure we wait, WaitGroup.Wait, WaitGroup.Add 5. And now let's go ahead and run these tasks as go routines. So let's say go task 1, pass in the address of the wait group. Let's duplicate this a couple of times, and let's rename this to task 2, task 3, task 4, and task 5. Now, in order to make it more interesting for our Go scheduler, we said we wanted to simulate a little bit of a difference in workload. So let's say, for example, task number 4 will wait a little bit, time.sleep 500, time millisecond, and let's say this one will slightly execute a little slower, let's say 600 milliseconds. And let's say task number 1 will be nothing else but an HTTP request, which will also simulate a little bit of load, and let's say say this one will be something like, let's say, crazy calculation, which will simulate a little bit of I/O on the CPU level. So let's go ahead and fill out the task number 2 first. Let's say, for example, we have a count variable. So let's say var count is going to be int. And now let's create a for loop, which is going to stress our CPU a little bit. So let's say for I is going to start from 0. I is going to go up to, let's say, 1 billion. So let's say something like this, which is going to be some crazy calculation for the CPU, but it shouldn't have any kind of problems. So let's say count, let's say plus equal with I. Next, let's go ahead and fill out the task number 1. And task number 1, we said is going to be an HTTP request. Now, in order to create a little bit of delay, we're not going to make an HTTP request to a real existing server. We're going to create our own server. But first of all, let's go ahead and make that request ourselves. So first of all, what we need to do is say http.get localhost, for example, and let's say 8080. And this is going to give us back a response, which we don't care about, and an error. Let's say we handle the error first. Let's say if error is not nil, let's say log.fatal, and let's say could not make HTTP request. And let's also provide in the original error and error. Now that we have all the tasks in place, let's go ahead and create that small HTTP server, which will actually respond to this specific request, which we make right here with a little bit of a delay. So on the same directory, I'm going to go ahead and create a new file called server.go. So let's say server.go func main. So in order to create our small HTTP server, let's go ahead and say http.handle func, and let's say / we want to execute this handler, and let's rename this to W and this one to R, just to stay a little bit shorter. And as I said before, we want to simulate a little bit of a delay, so let's go ahead and say time.sleep, let's say, for example, 300 time millisecond, and after that let's go ahead and say w.write header, and let's go ahead and say http.status. Okay, let's go ahead and run this, wrap this inside log.fatal. So let's say log.fatal, and let's say http.listen and serve, and let's provide in the address on port 8080, and let's provide in nil, which is going to make use of this default serve mux. So let's go ahead and open up our terminal and run this specific HTTP server we just created. So we're going to cd into go routines order and different workloads, and here we have main.go and server.go. So let's go ahead and say go run server.go, and this will run our server. And now let's open up a new terminal window and cd again into go routines order into different workloads, and let's say go run main.go. And as you can see, all these tasks will pretty much execute randomly. However, because we have different workloads, because those workloads will take specific amounts of times, you will see pretty much the exact same result. This is not a topic regarding tracing, regarding debugging. However, let's do a little bit of debugging. Let's run this example using Go's built-in debugging tools, just to check out how exactly things get scheduled, how exactly the Go scheduler takes this. So in order to run our example using Go's built-in debugging tool or tracing tool, which is going to emit scheduling events, we have to generate a binary out of this main.go file. cd into go routines order into different workloads, and here we have main.go and server.go. Let's say go build, for example, -o, and let's provide in an executable name. Let's call it exec, and let's say main.go. And as you can see, we have now a binary which is called exec. Let's go ahead and set up a couple of environment variables, and the first one is going to be go max procs, which will basically set the maximum numbers of CPUs which our application will make use of. So let's say go max procs is going to be equal to 1. Then let's go ahead and disable the garbage collection so that we don't get these events when we're going to do tracing. So let's go ahead and say go gc equals to off. And now let's go ahead and set up the go debug variable. The first argument we want to set up is schedule trace, and schedule trace is going to be equal to an interval in milliseconds, and this is how often we want the tracing tool to emit events. So let's go ahead and set this for 200 milliseconds, and let's also set something like schedule detail equals to 1, which will give us back a more verbose output. And now let's go ahead and provide the name of our executable, which is exact as we generated before. And when you run this example, as you will see, after each 200 milliseconds, our scheduler will try and emit a couple of data. So at the moment, I don't expect you to understand all this information, but what I want you to pay attention is at this the specific letters, so P, M, and G. So first of all, P's are usually your processors. This is the way it's called inside the Go terminology. So right here we specified Go max prox equals 1, thus we only have one processor, P0. And we have M's. M's are usually threads or machines as they're called in the internal terminology. And of course we have G's. G's are Go routines, which is exactly what we're looking for. So usually G1 will stand for the main Go routine. So what I want you to look at is not at 0 milliseconds, but at 200 milliseconds. Right here we have a little bit of a more interesting output. Try and focus on the rest of the G's, which is basically G9, G10, G11, G16, and G18. And as you can see, G9 is sleep, which is one of the Go routines which sleeps. And then we have another one, G10, which is also sleep. This is probably task 5. Then we have G16, which says IO wait, and this one is probably the one which does this crazy calculation. Again, as I said before, I don't expect you to understand all this information. We're going to cover this later on when we talk a little bit more advanced about concurrency and the way that's done in Go. And lastly, guys, let's go ahead and implement a wait group. You'll see it's so easy to build and fun. This is why let's not waste a lot of time and let's dive straight into it. So this is what a wait group needs to have in order to be implemented. It's a simple type which pretty much has only one field. So consider it a struct which has a field of counter, and that counter is some kind of integer. That type is also going to have 3 methods. It's going to have a method called add, another one called done, and another one called wait, just like our sync wait group has. So the add method is going to receive an integer and it's going to add that integer to our internal counter. The done method is actually going to decrement our counter by 1, and we have the wait method which basically infinitely waits until our counter reaches 0. This is a very dummy, very simple implementation of a wait group, but this is something which works. It's something which pretty much is implemented the same inside the sync package. So inside the same directory where we have all the examples, let's go ahead and create a new directory called wait group implementation. And again, let's go ahead and create a main file. Let's say main, package main, and func main as usual. So first of all, let's go ahead and create that type. So right here, I'm going to go say type, for example, wait group. And let's say this is going to be a struct because we need that field. So let's say counter is going to be int64. So first of all, we need a method called add, then another one called done, and another one called wait. So let's go ahead and say func, let's say w, and this is going to be wait group, and let's say add, and is going to be int64. Then let's go ahead and copy this because we need another method for done. So let's call this one done, and we don't need any kind of arguments. And let's copy and paste this and create another method called wait. So let's go ahead and fill out the add method first of all, where we're going to modify this internal counter right there. So let me actually rename the receiver and let's make this wait group. So I'm going to rename this to wait group. I'm going to do something like atomic.add in 64, and let's provide the wait group.Add counter. And then the second argument, as you can see, is the delta, and the delta is nothing else but the n which we receive as an argument. So this is pretty much it on the implementation on the add. And now let's go ahead and fill out the done method. All we really have to do is decrement the internal counter by 1 and also make sure the counter is not negative. Instead of using atomics again, we could say something like wait group.Add, let's say add, and we could use -1, and this will pretty much execute the statement, which is yet again atomic. Now let's check if the internal counter is not negative. If it's negative, let's go ahead and panic. If let's say atomic, and let's say load int64, and yet again provide the address. Let's say wait group.counter less than 0. In this case, we want to panic. Let's go ahead and say something like negative wait group counter. And now let's go ahead and fill out the wait method. And as I said before, the wait method is simply going to infinitely wait until our internal counter reaches 0. So let's go ahead and infinitely wait. We're going to simply have a check. Let's say if atomic, and let's again use load int64 and provide in the address, which is wait group.counter equals to 0. It means we have to exit. So we're simply going to return. Now inside our main function, let's go ahead and create an instance of this wait group type, which we just created. So let's say var wait group is going to be the wait group. This time we're not going to use sync.WaitGroup. And as usual, let's go ahead and say WaitGroup.Add. This pretty much feels very natural because it's pretty much implemented the exact same way as the sync.WaitGroup. So let's say we want to run 2 go routines, wait after that, and in between add and wait, let's go ahead and run our go routines. Let's say go func, and as usual, let's say defer WaitGroup.Done, and let's actually copy and paste this right there. And let's also go ahead and print something out. Let's say font print line, let's say go routine 1. Let's copy this, let's paste it over here, go routine 2. And also after we wait, print something like all go routines are done. So if you run this example, as you can see, it will actually print go routine 1 and go routine 2. Run it again, it's gonna print. If you want to modify this example just to make sure it actually works, let's for example go ahead here and say time.sleep, let's say 300 millisecond, and let's also go here and sleep for example for 500 milliseconds, just to prove you that this is not something which executes immediately. And run this example again. As you can see, it's going to wait, it's going to execute go routine 1, then go routine 2, then it's going to execute the statement inside main saying it's done waiting for those go routines. And this is pretty much it. This is pretty much it on this wait group implementation. As you can see, it's very simple to implement a wait group. However, we're not going to use this implementation of wait group because obviously the sync.WaitGroup has many more things to offer and it's built for us. We don't have to reinvent the wheel. This is why let's go ahead and have a look at how exactly that wait group is implemented. So inside the directory where we have all our example, I'm going to open up the basic example which we created before. So open this up, and as you can see, we have a sync.WaitGroup declaration. So if you hit Command or Control if you're on Windows and click on this wait group declaration, as you can see, it's going to redirect you to the standard library. And as you can see, this is the type declaration of the actual implementation of the wait group. And we have something like no copy. And as you can see, we also have something like state. And then we have, if you scroll down, we have our very common methods, which is add and which is also done, and which is also wait. What I like to do is a lot of the times look through the standard library, through the way how it's implemented, what exactly is causing specific errors, specific panics and all that stuff, and how to mitigate them. Hope you guys enjoyed this. This is a little bit of an extra mile, which I'm not sure was worth it, but hope you guys enjoyed it. Hope it was fun for you to implement a wait group from scratch. So usually you know how many go routines you want to wait for. This is why I recommend using add with a bigger argument instead of calling add with the argument of 1 multiple times. But don't just hear what I'm saying. Let's go ahead and play with a couple of benchmarks to prove you that executing add this way is a little faster, and in some scenarios this can give you a little extra performance boost. So again, back to our directory where we have all our examples. Let's go ahead and create another one. So let's say directory, and let's call this one benchmarks. And inside of this directory we're going to create a test file. Now we haven't covered benchmarks or testing before, but we're slowly going to cover a little bit of benchmarks because we're going to heavily do benchmarking in this course. This is why in order to create a test file, all we really have to do is give it a name and make sure it ends with _test.go. So let's create a file and let's call this one add one underscore versus let's say underscore add many underscore test.go, and it has to be ending with underscore test.go in order to be recognized as a test file. And as you can see, we even have this inside the IDE. We have these small little icons. And now let's go ahead and create the actual benchmark. So in order to create a benchmark, it's fairly easy. Func, and it has to start with the word benchmark, and then it can be followed by really anything. So let's say benchmark add one. It has to receive an argument called b. So let's say b is going to be pointer to testing.b. So this is the way we declare a benchmark. And as you can see, we have this small little green arrow, which will allow us to run this benchmark. So first of all, let's go ahead and create a variable, which is going to be count. So let's say var count, for example, and let's make this an int. Then as usual, let's go ahead and create a wait group. So let's say var wait group. It's going to be a sync.WaitGroup, and normal procedure WaitGroup.Wait at the end of it. So the beauty about this b variable is the fact that it's going to give us access to many things, including something like n. So n is going to be the number of iterations. And now let's go ahead and create that for loop. So let's say for I is going to start from 0, and this time I is going to go up to b.n, which is that number of iterations. since it's going to be variable, it's going to always increase, having the n increase all the time. So let's say I++. And now inside the for loop, let's simply go ahead and say WaitGroup.Add, and let's provide in 1 because this is what we're benchmarking. And now let's go ahead and run a go routine. So let's say go func, and let's, as usual, say defer WaitGroup.done. And let's actually go ahead and do some work. Let's, for example, increment this counter. So this is pretty much it for this benchmark. Now to make the other benchmark exactly the same, all we have to do is just copy and paste this and do a couple of adjustments. So first of all, let's go ahead and rename this. Let's name it benchmark add many. So I'm going to go ahead and cut this and put this right after the WaitGroup declaration. And instead of 1, I'm going to place something like b.n. And this is always going to change every time this function is going to get called by the testing framework. So this is exactly the same function. Notice we didn't change anything. All we did change was the way we call the add function. As I said, this b variable has many interesting things, including something like report allocs. So report allocs will basically report how many allocations per operations were done. And now, ladies and gentlemen, it's time to go ahead and run our benchmarks. So let's go ahead and open up a terminal and of course cd into benchmarks. And we have this little benchmark file. And all we have to do is simply go ahead and say go test, and let's say -bench, and -bench is going to ask for the directory, which is going to look for benchmarks. So we want to provide in the current working directory, which is dot. So if you do that, as you can see, because I'm using Go version 16, it's going to complain because it wants us to run Go modules. It's going, including the Go test command, is going to run in module aware feature. This is why, just for the sake of running this benchmark, I'm going to go ahead and say go mod init, and let's just provide something like benchmarks, and it has created this go mod file. And now let's go ahead and run the exact same command. And when you run this command, as you can see, it's running the benchmarks. So as you can see, we have a very slight performance improvement where it says benchmark add many. If this number is bigger, it means it ran more iterations. And also if this number is smaller, it means it took less nanoseconds per operations, which proves that it's a little bit faster. So as you can see, we have a small gain of about 200,000 iterations, and also a small gain when it comes to the nanoseconds per operations. So this is pretty much it, how you do benchmarking. Hope this was interesting. Hope this was something useful. And yeah, as I said before, most of the times you will know the number of concurrent operations you want to wait for. This is why just stick with this option. All right, guys, so this was pretty much it on the third part. This was pretty much it on this topic regarding wait groups. And of course, before we wrap this video up, make sure to head over to that GitHub page where you can find downloadable zip archives. I know we've gone through a huge amount of information, and perhaps for some of you it has been fun. It has been a very valuable piece of info. Now, if you found this video or any video on this channel useful, valuable, make sure to hit that like button and share this video. And of course, if you're not part of this community, make sure to hit that subscribe button over there. And speaking of community, make sure to check out the Discord server, which of course you can find in the video description below. And lastly, guys, I've been doing YouTube full-time for about 4 months already. So if you feel like contributing, if you think that this project which we're doing deserves your contribution, head over to my Patreon page and you can do it over there. Or you can do it in a one-time donation via PayPal. So yet again, this was pretty much it on this topic, pretty much it on this specific video, and I'll see you guys in the next video regarding concurrency in Go. Peace!